Pietro will tell us about the open story.
Okay, yeah, thanks. Again, thanks to Giulio and Alessandro for organizing, once again, this very nice workshop and the opportunity to contribute. So, yeah, I will tell you about a continuation of what Maxime has been talking about. And this is really about the paper that came out roughly a week ago with Luca and Maxime. So, so the main question that we tried to address was, well, how to model A-branes, so an object in topological string theory, from the viewpoint of the world sheet. So that's an old subject, but surprisingly, actually not so much progress has been done on this question, although previous works do exist. And well, first of all, why is this question important? Why is it interesting? Well, let me give you some motivations. One of these that you may be familiar with is the topological vertex. So the topological vertex is a fantastic combinatorial object. And, well, it's being used to obtain exact results about open and closed strings in the context of toric Calabi-Yau threefolds. It has applications to supersymmetric gauge theories and many more topics in mathematical physics. But intrinsically, the definition of the topological vertex is that it really counts open string instantons to all genus with boundaries on certain Lagrangian submanifolds or A-branes in the simplest of toric Calabi-Yau threefolds, C3. However, the definition does not match the way it was computed. So the computation of the topological vertex was not done by direct worldsheet analysis. Rather, it was obtained by large N transitions. So there's no, well, as far as I know, there's no direct derivation in the physics literature of the topological vertex as something that comes out of a honest worldsheet computation. So it's not so obvious if you look at the expressions that come out of the vertex. Sometimes it's not so obvious how exactly you should interpret them from the viewpoint of curve counts. But if you count from this perspective, then this gets clarified quite a lot. Another motivation for why it's interesting to study A-branes is applications to the relation between physics and knot theory. So there's a whole there's a whole line of work that studies the relation between mathematical physics and knot theory that starts with Chern-Simons theory, but then through a chain of dualities arrives at looking at a certain class of A-branes modeled on Lagrangians in the resolved conifold. And these Lagrangians, they retain some information about knots. And through this relation, people have come up with some interesting predictions about structures of knot invariants, including not only polynomials, but also homologies. But once again, this relation is not quite computable from the viewpoint of the worldsheet. You can only, well, so what people usually do is they use knowledge of knot invariants computed by some other means to deduce some information about open string instantons in the presence of these Lagrangians. So once again, if you want to understand where all these structures and properties come from, you really need to start trying to understand how to think about these A-branes, in this case the ones pertaining to knot theory, from the viewpoint of the worldsheet. I'll just give you a third reason why you should be interested in this kind of question, which is that A-branes are objects in something called the Fukaya category, which is some mathematical framework to describe topological properties of how certain types of branes behave, how they interact among each other, how they decay, form bound states, and so on. And again, one of the key drivers of the dynamics of this type of branes in the Fukaya category is something called an A-infinity structure that's ultimately tied to understanding how open strings end on these branes and what they do when they couple different branes together. So there's many different reasons why, at least we think this question is interesting. And today we're not going to answer any of these very ambitious questions, but we're going to focus on a universal class of A-branes that is actually related to the first question, the topological vertex. And so I'll start by reviewing a little bit the topic of toric branes. So the target of the talk will be to understand how to compute well-sheet instantones in genus 0 for toric branes in all toric labial threefolds. That's what we want to do by the end of this talk. And we want to do it from the viewpoint of the well-sheet. So toric branes, as I said, is a universal class of branes in topological strings on toric calabial threes. So toric calabial three, as Maxime reviewed, it can be described as a symplectic quotient of just flat space. And just to set some notation, let me remind you what this means is that we take C R plus 3, we have a group action by an abelian group that just rotates the coordinates according to some charges, QJA, alpha A, ZJ. So here the indices A goes 1 to R and J goes 1 to R plus 3. And then the symplectic quotient is defined by, so XT is defined by taking the level sets of the moment map, meaning we take sum over J from 1 to R plus 3, ZJ absolute value square times QJA equal TA. So that's the coordinates of the moment map for a Hamiltonian U1R action. And then we take a regular quotient by U1R, and the idea is that for generic values of the T's, these are real parameters, the T's. For generic values, this gives you a smooth symplectic manifold. That's basic construction in symplectic geometry. Now, if you want to get a Calabi-Yau, one condition you have to impose is that the sum of these charges is equal to 0 for each of the U1 factors. So what that gives you is that the canonical bundle of the resulting quotient is trivial, and then the metric is not Ricci flat, but it will flow to a Ricci flat metric if you do string theory on these spaces. So I'm going a bit fast because Maxime reviewed all of this, but if something is not clear, just stop me. Okay, so we want to understand toric branes in this setting. And one thing that's really helpful is to give a specific presentation of these toric threefolds. We want to think of them as T3 fibrations, which is not entirely the usual way that people think about them, but it's fairly intuitive. So there's a T3 fibration over a three-dimensional base. So let's give some examples. So this is called a moment polytope. And so, okay, the simplest example is C3. One can think of as T3 fibration over just the positive octant of R3. So this is what the moment polytope looks like. Coordinates Z1 square, Z2 square, Z3 square. For the resolved conifold, we have R is 1. The charge matrix is 1, 1, minus 1, minus 1. And then the moment polytope will be defined by 4 hyperplanes, like that. And then there's another example that's fairly standard, which is local P2, where the charge matrix for the U1 action is 1, 1, 1, minus 3. And the moment polytope is, again, 4 hyperplanes. The intersection of 4 half spaces looking like that. Okay, it's just a T3 fibration over three-dimensional base. So now, if you think about these Calabi-Yau threefolds in this way, then it's really easy to define what toric Lagrangians are. So it's a construction due to Harvey and Lawson from many years ago. And let's see, there's no color chalk. Okay. Maybe there is. Is there any? No, it's fine, but I'll just use dashed lines. That's fine. Uh, so, um, so then what you do to define a toric special Lagrangian is you choose an affine half-line. I'll call it L. So this will be an affine half-line in the positive orthant of the ambient space. So this will be in R positive to the R plus 3. Okay? And then over this line, which we're going to take with slope 1, 1, 1. Okay? So we have R to the R plus 3. We just take the positive orthant. And then we take any line that does not have to go through the origin. That's what affine means. And it has a slope, which is 1 along all directions. Okay? And then, so along this line, you take a torus, T R plus 2, defined by the condition that the phases of all the complex coordinates add up to 0. So theta 1 plus theta 2 plus theta R plus 3 is equal to 0. So this gives you a manifold that has real dimension R plus 3 now. If you take this torus fibered over the half line, let's call this L tilde. What is theta? Yeah, I'm being a little bit sloppy. So theta for me is the phase of the complex coordinates. So Z, right? But in the ambient space. Okay. So far I'm working in the ambient space. I get this manifold, and then it's a very simple exercise to show that this manifold, which is locally TR plus 2 times the affine line, is in fact a special Lagrangian. Special Lagrangian means that it's Lagrangian, the restriction of the symplectic form vanishes, and special Lagrangian means that the restriction of the holomorphic top form is a positive multiple of the volume form. Yes. Yes.
So you said that there are no rich flat metrics, but they float rich.
Well, in general,
Yeah,
if you pull back the
they exist.
yeah, right.
Is it the case of hyperkähler cases or which one? Which are distinguished when these metrics exist?
No, so the statement is if you take this construction, right, this quotient gives you a symplectic manifold. It's a three complex dimensions, so it's not going to be hyperkähler.
So you restrict to 3 complex.
Yeah. In this talk, we're going to do 3 complex.
So there can't be any hyperkähler.
No, they will not be hyperkähler. Well, okay, some examples of toy examples will be, but that's not the main. Yeah. And of course, if I just take C3, well, there's no quotient, nothing. That's of course that's pretty richly flat. That's as flat as it gets. But yeah. Okay. Yeah. Right. Okay. But so far I've defined for you a Lagrangian in the ambient space. Then the claim is that when you pass to the quotient, right? So maybe I'll write it here. So you pass to the quotient x c r plus 3 quotient u1r, then this L tilde descends down to a honest special Lagrangian. So you get a special Lagrangian L, which locally looks like T2 times the projection of the affine line. So the quotient kills some of the circles in the R plus 2 torus, but it leaves you with T2 times L. Okay? And right, so let's maybe give some example of this, some basic example. So in C3, we can describe such a Lagrangian by a couple of equations. So we have Z1 square minus Z3 square equals C1, Z2 square minus Z3 square equals C2, and theta 1 plus theta 2 plus theta 3 equals 0. Okay? So that's the most basic example of such a construction. So the first two equations define my affine half-line. So in C3, R is equal to 0. I don't have to take any quotients. But then if I choose coordinates Z1 square, Z2 square, Z3 square in the moment polytope, then if I choose, say, C1 positive and C2 positive, then my affine half-line will be described by the first two equations. It will land at Z3 equals 0 here at this point, C1, C2, and then it will give me some ray of slope 1, 1, 1. And then along this ray, I take this torus that's locally parameterized by a subtorus. So remember, this is a T3 fibration, but then this defines a subtorus with local coordinates, which I can choose like this. And I get these two torus everywhere along this line. So if I do that, I get a Lagrangian that, as promised, looks like T2 times R. It's a special Lagrangian. But then what we really want to do actually is we want to... Sorry. Yes, it's very easy to see it's Lagrangian. You just write the symplectic form in... so the symplectic form would be something like this. And then you pass to polar coordinates, okay? So this is going to be something like d theta I wedge d z I square, right? And now what's crucial is that I require that my line has slope 1, 1, 1. And the torus I take to have exactly, so it's orthogonal to that hyperplane. So that's why it's special. So this is a general construction. It's much more general. You can build manifolds of all sorts of types using this kind of trick. They're always Lagrangians. It's due to Hagen-Lawson. Okay, very good. So that's, so in fact, sorry, to be Lagrangian, you don't even have to specify to this slope. It could be any rational slope, and then you choose the corresponding dual torus. But the reason why 1, 1, 1 slope is important is because you also want it to be special. So then if you study the restriction, the pullback of the holomorphic top form, that's the condition that tells you that it's going to be positive multiple of the volume form. So the slope has to be that. Okay, so we want to specialize this now a little bit. I'm going to set one of these constants to be 0. So I'm going to set 0 here, and I'll call this C. Okay, so then I'm moving this Lagrangian over to here. Okay. And if I do that, then something special happens. So you still have the T2 generically along this line, but then the T2 now degenerates here because you see that Z2 also goes to 0. So this angle doesn't make sense. And so the torus shrinks to a circle, and this Lagrangian changes topology. It's no more T2 times R positive. It's actually R2 times S1. Okay? And so that's important because there's a theorem about special Lagrangian submanifolds that tell you that the moduli space has dimension equal to the first Betti number. In this case, it's 1. So this has a one-dimensional moduli space. And the moduli space, in fact, is the space of deformations parameterized by C. So you can move this up and down along this edge of the moment polytope or along the other edges. That's the moduli space of this Lagrangian. Now, there's a fairly obvious fact that will nevertheless be very important later on, which is that I can think of this Lagrangian as being defined by this affine line, but in fact, I can think of this affine line as the intersection of two hyperplanes. So one hyperplane is this one, and if I picture that hyperplane here, it's going to look something like this. Whereas the second one is going to be something like this. Okay, so that's simple algebra, right? Line is intersection of two hyperplanes. But the point is that these two hyperplanes intersect along my line that defines the Lagrangian. And notice that one of the hyperplanes is homogeneous, but one of them is affine. And it's the affine hyperplane that records the information about the moduli of the Lagrangian. So this will play an important role later on when we talk about cuts. So for now, the main message here is that you can define Lagrangians this way, and somehow they're associated canonically to some choice of affine hyperplane. Now, I gave you this example in C3, but of course, the story is very general. As you probably know, you can put this Lagrangian on any one of the legs of the diagram, and this construction generalizes to all toric labial threefolds. And then the next thing we want to do is we want to think about branes, so A-branes, modeled on this type of Lagrangians. And what this involves is the additional data of a U1 flat connection on L. So in physics, we say there's a Chern-Simons theory living on the brane. And because B1 is equal to 1, this flat connection will have one modulus. So it has S1 moduli space. And so when we think about branes, the actual moduli space is a circle fibration over the moduli space of the Lagrangian. Except that at the origin at the vertices of the moment polytope, the topology of the Lagrangian degenerates, the S1 shrinks, so the holonomy doesn't make sense. And so it's actually a union of cones over the moduli space of the Lagrangian. That's the moduli space of the Lagrangian with a U1 flat connection. That's a classical story. And then there's a well-known story that when you do string theory on these A-branes, the moduli space gets corrected by genus 0 well-sheet instantons. And the claim is that the true moduli space of the A-brane, and here we're only looking at genus 0 instantons, the true moduli space is a Riemann surface. That's a resolution of this singularity. The resolution comes about because when you take the brane very close to the origin, the holomorphic disks that end on the Lagrangian go to 0 area, so they become more and more important. And then the claim is that their contributions altogether, they end up in this smooth structure. And Aganagic and Waffa came up with this proposal with some refinement due to Aganagic, Clem, and Waffa. And the moduli space of the A-brane can be described, according to these authors, by a simple algebraic curve. In this case, that is the curve that describes the toric brane in C3. Now, the point of this statement is that if you believe what they say, if you believe that that well-sheet instantons deform the moduli space in this way, then you may expect that. Yes.
These are the Lagrangian branes that you obtain by putting C1 to C and C2 to C.
Yes, yes.
And the others?
The others, you mean on the other legs?
No, yes, I mean, there are other Lagrangian branes.
Well, others, yeah. I mean, you can build all sorts of Lagrangian submanifolds of C3.
Topologically, T2 cross.
That's right. Yeah, that's right.
Okay, and so those ones don't.
No, they don't have this property, absolutely, because those would be, well, first of all, there's many technical details there. So first of all, you have to continue this affine half-line, otherwise you have a boundary in the middle of space, right? You're gonna have a T2 boundary. That's one thing. But then even if you double up this affine half-line and you go through, the topology of those will be T2 times R. So that tells you that the moduli space of those would be two-dimensional because B1 is 2, right? So that's a whole different story that, as far as I know, hasn't been developed. So these are the simplest ones. Yeah. This is
There are other
absolutely
other branes which end up on those other.
right. Yes. Yeah, that's right. Okay, so now if you take this statement as is, what this is saying is that somehow this algebraic curve knows all about the genus zero string instantons, and in fact, these authors they tell you how to recover the worldsheet instantons. So there's a formula for the so-called disk potential. I'll write it here. So they tell you that the disk potential for this A-brane model on L is the integral of log y d log x, where y of x is the solution to this algebraic curve. And in this case, this boils down to Li2 of minus x. Okay. So this is the case in C3 for toric brane in C3. Now, as I said, this derivation, this claim, doesn't go through the worldsheet. The arguments that are involved in this claim are based on open string mirror symmetry for local Calabi-Yau threefolds, and so they're somewhat indirect. It's a highly non-trivial prediction, but what we would like to do next is we would like to see how to compute this directly from looking at the worldsheet in C3. Okay, so that will be the goal. How much time do I have? Let's see.
In this case, in C3,
yes.
What are other A-branes? Some linear, they will given by linear equations.
Well, that's a class of A-brane. So you would have, right? So you would have, for example, this brane. You can move it on other legs. That's very similar to this one. It's captured by the same moduli space, of course, right? Yeah. Then you have another class of A-branes that Julie was asking about, where I did not put. So if you don't put C2 equal to 0, you have a whole different class of A-branes that just move around, where the moduli space is two-dimensional because their topology is B1 is equal to 2. But these are only like the simplest ones, right? You can cook up much more general types of A-branes. For example, if you think about, so if you're familiar with this relation to knot theory, there you have some branes defined in the resolved conifold from large N duality. They have a particular shape that intersects, the three sphere at infinity in the fiber. So in the resolved conifold, you have a fiber that is isomorphic to C2. The boundary is a three sphere, and these branes intersect the three sphere on a knot. So that's why they're associated to knots. Now you can take those, you can send T to infinity in the conifold, and they descend to very fancy A-branes here in C3. That's another class, but yeah, there's many.
Well, beyond worldsheet, you say that you will give us worldsheet definition at certain point, yeah?
Yeah.
Some boundary conditions or something.
Yeah.
But here, is there any some generic definition of what is a brane in this language, in analytic language?
Well, so A-brane at this point means a Lagrangian.
Yeah, but it's not constructed. Yeah?
No, it's not constructed. Yeah. So again, it's a little bit like the story that we discussed earlier, that you take C to the R plus 3, you do the symplectic quotient, you get some symplectic manifold. It's not Calabi-Yau. But then you say, oh, once I do string theory on that, there's going to be instantons that deform the moduli space and turn it into a honest Calabi-Yau manifold. Here, the spirit is exactly the same. You start with whatever, C or some Calabi-Yau. You take a Lagrangian that you can do. The moduli space of the Lagrangian is this union of lines. It has some vertices where the Lagrangian degenerates, and then you put a U1 flat connection. Still, the moduli space has some singularities. But then you say the words, I'm going to do string theory, and worldsheet instantons are going to do something nice for me, and we're going to see that that's true. But the way that these people derived it is by some very smart arguments involving local mirror symmetry, going to the B model, holomorphic transitions, and so on. But okay, we want to do something much more down to earth and try to understand this formula from first principles. Very good. So that's the goal. We would like to now find a way to reproduce this kind of formula, in fact, generalize this kind of formula for all toric branes in all toric threefolds. And so what I'm going to do next is I'm going to,
Sorry, just a question about this formula. Is there a 3D equal to interpretation?
Yes, there is. Yes. Yeah. It's a free chiral. That's right. Yeah, that's right. Or a U1 with a charged chiral.
In the direction of the 2x.
Yeah, that's right. Yeah, you put say an M5 on the Lagrangian inside C3, and then by 3D correspondence it gives you a theory on the three transverse directions, and that's the um, effective twisted superpotential of the 3D theory on S1 times R2. Okay, very good. So now how are we going to do this? So we're going to need to introduce this new tool, which is called a symplectic cut. So symplectic cut is actually a fairly old construction. It's one of the most basic constructions if you ask a symplectic geometry. It's a little bit like the symplectic quotient. It's not really anything too advanced, but perhaps a bit unfamiliar to us. So let's review what it is. So let's say you have a symplectic manifold, and we'll just illustrate this with a simple example, which is what Maxime did. So we take C2 with a standard symplectic form. And then let's say on the symplectic manifold you have a Hamiltonian U1 action. Okay, so and in this case, so Maxime explained what Hamiltonian means. So in this case, we take this action to be Z1, Z2, go over to e to the I alpha Z1, e to the I alpha Z2. And Hamiltonian means that we have a Hamiltonian for this, or moment map in this case, they coincide, which is Z1 square plus Z2 square. Then, okay, so one basic thing we can do is we can consider the symplectic quotient. So in this case, mu equals C mod U1. As Maxime said, this is S3 times S1. And as a symplectic manifold, this is P1. And what this is doing for us is we're looking at C2, right? The moment map condition gives you a submanifold of codimension 1. That's S3. So here we have, so this is the T2 fibration, right? T2 fibration of C2. We have a 2 torus fibered everywhere, but the A cycle shrinks on one side, the B cycle on the other side. So this gives you the S3. And then when you take the quotient by S1, this 2 torus is replaced by a circle, but the circle now degenerates, and that's your P1, right? So that's a fairly standard story. But now, once you have this, you can do a little bit more. You can define m greater and m less as the two half spaces in the full manifold, not in the symplectic quotient, but in the full manifold, where the values of the moment map are greater or less than C. Okay? So m less will be here, m greater will be here. And these are full dimensional objects. So m less will be topologically, in this case, it will be a four ball, right? It's just the origin of C2, where you have a 3 sphere at the boundary. And m greater will be topologically something like S3 times R positive. Okay? So you can take those spaces. It's just a basic definition. And now, what is the symplectic cut? So now I can define for you what is a symplectic cut. So the symplectic cut of this manifold at M0.
Sorry, Pietro, but
yes.
they are topologically different because one of them contains the origin.
Yeah, that's right. Yeah, exactly. So, so if you take mu of z less than c, right? So that means this thing less than c. That's a 4 ball. But if I take it to be greater than c, that's the complement of the 4 ball. And that's this thing. It's just 3 times R positive. Good. Okay, so yeah, so the symplectic cut of this manifold at M0 is defined as the union of two objects, m minus bar and m plus bar, over n0, where this m minus bar and plus bar are defined in a very simple way. I'll give you the intuitive definition and later the formula. So basically, to define these two objects, you take these two guys that we defined, m greater, m less, and then you take a U1 quotient, but only here at the boundary. So both of them have a boundary here that is S3, right? And if I take the quotient of B4, the 4 ball at the boundary, then I still have a 4-dimensional manifold. But the boundary used to be 3-dimensional, then it gets contracted to a P1. Okay? And the same thing I do here outside. I have a boundary that's S3. It's a 4-dimensional manifold, and I contract the boundary. So I do something called a real blowdown, if you wish. But anyways, so that's the intuitive definition of these objects. Now I'll give you the actual definition. So let's stick to our example. So what we do is we introduce an extra direction, and we define a space Z, which is n times C, and we extend the symplectic form to the standard one. So C has coordinate W now. And then we extend the U1 action. So there's a U1 action on this extended space that takes my coordinates, and it rotates Z1, Z2, again, in the same way as before, but it rotates W with the opposite orientation, with the opposite phase. So then I have a moment map for this U1 action. I'll call it mu plus. That's Z1 square plus Z2 square minus W square. And the definition of m plus bar is the symplectic quotient by this U1 action. So so you take the moment map, you set it equal to C. C is the same that I'm using here to define M0. And then I take the quotient by U1. Okay. And now let's think about what this space looks like. So I told you that this should now look like this M positive, where I just take a U1 quotient at the boundary. So let's see how that comes about. So if you take a point at W equals 0, then you see the moment map, when I set it equal to C, well, I get Z1 square plus Z2 square equals C mod U1. Well, that's exactly M0. So the boundary of this manifold indeed is P1, just like I promised. But if W is non-zero, well, maybe I need more space. So if W is non-zero, then my moment map is saying the following. It says that Z1 square plus Z2 square is equal to C plus absolute value W square, right? And then I take a quotient by U1, right? That's just the definition of M plus bar. But this means that we're looking at some manifold where Z1 square plus Z2 square is definitely greater than C. So then this space looks like M positive for each value of W. But in fact, I'm only fixing the absolute value. So I have a circle related to the phase of W. So that's the topology of this space. It's M greater times S1. And then when I take the quotient by U1, well, what it does is it takes a quotient according to these charges. So it's going to reduce this now to a 2-dimensional manifold. And actually, that's a very familiar one, right? You should recognize it from here. This is just O minus 1 over P1, right? So that's what it is. And likewise, there's a similar definition for M minus. So it's just defined with the flip of the signs. So you take Z1 square plus Z2 square now plus W square equals C modulo 1, and you recognize that this is just a description of P2 as a symplectic quotient of C3. So, so what I've defined then is now something like this in this example. So we started with C2, coordinate Z1 square, Z2 square. We introduced an extra direction, that's W square. And then inside C2, we had this symplectic quotient, which I call M0. And now in this bigger space, we defined some locus defined by these moment maps. And this locus looks as follows. So it's going to be a triangle here, and the continuation of this triangle in the positive half. Okay. So this is m bar plus, this is m bar minus, this is P2, this is O minus 1 over P1. And as promised, you get two complex dimensional manifolds. And each of them has a divisor, which is a P1. So it's a hyperplane in P2, and it's the zero section in O minus 1. And the idea is that these two manifolds can be glued together along this P1. So it looks like a funny operation to do. Yeah.
With this M minus bar, we just change the sign in front of the
Yes.
W.
And in the U1 action.
Is it just some general definition? Or
Yes. Yeah. Yeah.
You define mu plus, but no minus. Yeah.
Well, no. So I define mu plus here, and then I say, okay, mu minus is defined by flipping the sign.
By flipping the sign.
Yes. So this is a general definition. So here I gave you an example, but in general, what you would do is you would define this as the old moment map for this Hamiltonian U1 action on the original space, minus W if you were doing M plus, and plus W if you were doing M minus. That's a general definition of the symplectic cut. Okay. Very good. So this is something that symplectic geometers defined 30 years ago. It turns out that although it looks a little bit funny to glue two manifolds on a complex codimension 1 locus as opposed to a real codimension 1, it turns out that it's a very natural thing to do from the symplectic viewpoint. So many properties of the space you start from are related to the properties of this space. So this is a new symplectic manifold, and there's ways to go back and forth between the properties of the original one and this one. So that was a toy example, just to tell you what symplectic cuts are. Now we want to do this in the context of Calabi-Yau threefolds, but luckily the story is very, very similar. And it's very simple to understand if you get this one. So cuts in Calabi-Yau threefolds are just defined as follows. So you have your favorite toric Calabi-Yau threefold with an additional U1 action now. Let me call mu the moment map for this U1 action. And then the symplectic cut of this is the union of something called x plus bar with x minus bar over x0, where x0 is the symplectic quotient of x by this U1 action. Okay. So in practice, what this means is that if you have some Calabi-Yau threefold to begin with, then the moment map for the U1 action will define for you something like a hyperplane. Okay. And then the cut happens along this hyperplane. So you have a T3 fibration in the bulk. But then once you cut, the T3 degenerates to a T2 here on the cutting locus. Just like before, we had a T2 degenerating to a circle on the locus. Now we have T3 degenerating to T2. So again, we have two three-dimensional manifolds, three complex dimensions, glued along a two complex dimension locus. And now you may remember that this kind of hyperplanes arise when we think about toric branes. So now I told you that toric branes are associated to affine hyperplanes. And I also told you that affine hyperplanes define very naturally something called the symplectic cut. So there's a natural way to associate symplectic cuts to toric A-branes, and it turns out that it's a very interesting thing to do is to study string theory in this setting. Right. Okay, so I have to speed up a little bit, but right. So now comes the new part. Well, the interesting part, but I don't know. Let's see. So now we want to talk about quantum cuts. Quantum cuts, which means we do string theory on the cut, right? So what does it mean to quantize geometry? So I'm going to follow Maxime's talk. It means we take a GLSM.
Point out that the volumes from the left and right cuts give was a full volume.
Yeah, I was maybe going to say this later, but that's right. So one of the nice properties about these cuts is that, well, at least you can do this at many levels, but for example, in the equivariant setting, right? Here you get a hyperplane that's non-compact, the volume is infinite, but in the equivariant setting, you can define a volume. So you can define an equivariant volume for this x0, right? It's a regularization of the infinite volume. That's defined by the equivariant integrals that Maxime was discussing at the beginning of his talk. And then you can define the equivariant volumes for the two half spaces. And well, the symplectic cut is nice. It plays very well with equivariance because you can show that, in fact, there's two interesting statements. So one of them is fairly obvious, that the equivariant volume of the full space, so before you cut, is actually equal to the sum of the equivariant volumes of the two half spaces. But more importantly, for what we're going to say later on, is that you can also show that the volume of x0 is actually a measure. So now I'm getting a little bit ahead of myself. Thanks, Maxime. Okay, I'll just mention a trivial fact. We'll get to the more interesting one in a moment. But okay, so
Is it a trivial statement or not? Like it's written on the picture, yeah, it looks like trivial.
Yeah. Intuitively, it's trivial, right? And of course, it's trivial if you're in the compact setting.
It's not trivial because you write the volume of C2 as the volume of P2 plus the volume of
yeah, right. Yeah.
So in this sense, it's very weird expansion, but it's of course not trivial.
Yeah, and of course, I mean, the reason why it works is because everything here behaves nicely under the U1 rotations of the various, of equivariance. But yeah, it's a bit non-trivial because everything in this particular example is non-compact. So you may ask, well, before you ask, like, what definition of volume is this? What does it correspond to classically? And maybe there's no obvious definition, but it's a definition that has some nice properties. For example, it behaves nicely under cutting. If you apply this equivariant volume definition on both sides, it's compatible with the one in the bulk.
Is it true that the equivariant volume of this x0, if you divide by equivariant volume of something bigger, goes to 0? So that it's negligible compared.
You want to say it's measure 0.
Yeah.
So there's a better way to state what you asked, and that's actually the fancy formula I wanted to. Okay, yeah, I'll just write it here. So the statement is, it's not hard to see that the equivariant volume of X, the uncut manifold, is equal to the integral of the equivariant volume of X0. So this is like a Lebesgue measure for the full volume. So that's another very important and very useful relation that we're going to make use of. But you see, again, this tells you that whatever these equivariant volumes are, they have some very nice properties, right?
Moving x0
Exactly, exactly, exactly. Yes, you can move it. Yes. So if C is positive, maybe it's going to be here. If C is negative, it's going to be there, and so on. But then you sweep across the whole manifold. Exactly. That's the right picture to have in mind. But now I'm going to have to give you the physics part of the talk.
This formula is incredibly trivial because you put the moving part and click the breakable value.
Yeah, yeah. But we didn't do any physics yet. Come on, let me just some basic math. Let's try to say something a little bit more interesting now. So the quantum cuts. So as Maxime was saying, to quantize geometry for us, it means to take a GLSM from R2 into X. Okay. And because we have an open worldsheet, we have to specify the boundary conditions, and we take a space-filling brane, which means that the boundaries of the worldsheet can end anywhere, and you will see effects of that. And then one can write down the partition function, one can localize, and Maxime wrote down this very nice formula. So product A from 1 to R, d phi A over 2 pi I, e to the sum over A, phi A, TA, and then a product of gamma functions of epsilon I plus QIA phi A. So we discussed this before. This is after localization. That's the contribution from the U1R gauge group. These are the Fi terms, and this is the matter fields, the one-loop determinants of matter fields, where equivalent parameters play the role of masses, and the QIA are the charges of the matter fields under the gauge group. The space-filling brane? Yeah. Well, it means we don't impose any conditions so far. Yeah, just no condition. Yeah, that's right. So far, I'm just recalling what Maxime said. I haven't introduced branes yet. Right. And another important point that Maxime made is that if you take the semi-classical limit, right? So semi-classical limit, what you call lambda goes to infinity, then this quantity recovers the equivariant volume of the full Calabi-Yau. And the idea is that all the maps restrict to constant maps, and then the moduli space of those is the equivariant volume. Very good. Yeah, you put more. Yeah. Sorry. Okay. So another nice point to keep in mind is that so this relation tells you that the partition function of the GLSM you can think of as a quantum volume, meaning it's to leading order in lambda, it's going to be the equivariant volume, but then you have the instanton corrections. And the important point to keep in mind is that this quantum volume is very well behaved. It's analytic in the T's, for example, whereas this one is not. So, for example, it has a cusp discontinuity at t equals 0 in the case of the conifold, as we've seen in one example. And this one you cannot expand, therefore, at t equals 0. There's no expansion at the conifold point. There's only large volume expansions. But this one you can even expand at the conifold point. So anyways, going over to the quantum story makes things a lot smoother and nicer. But now what we want to do is we want to introduce branes, right? So we're going to do quantum cuts, meaning we take GLSM from R2 into the cut manifold. And so there's a basic quantity that you can naturally compute, which is the quantum volume of the gluing locus. So the gluing locus will be some two-dimensional complex submanifold defined over the hyperplane where you cut. And so this will be a quantity that we call HD. It will depend on the closed string moduli, so the Kähler moduli of the Calabi-Yau. It will depend on the open string moduli that parameterizes the position, the transverse position of this hyperplane where we cut. And it will depend on the equivariant parameters. And so it's defined in the usual way. It's a product over the gauge group, but now the gauge group is rank r+1. And then we have the Fayet-Diopoulos parameters as before, plus a new parameter, phi r+1 times c. Okay. And then we have the matter fields as before, but now these matter fields, they're charged not only under the gauge group that defines the original Calabi-Yau, but also under the last gauge factor. So this charge matrix is extended to include charges under the last U1, the U1 that defines the symplectic cut. So now, by general statements of what Maxime said, it follows that if you take the semi-classical limit, lambda goes to infinity, this reduces to the equivariant volume of the cutting locus, right? This, which may be non-compact, but still with equivariance you can make it finite. And once again, you find that this is not analytic in the Kähler moduli, but this is. So this is nice. This is very well defined, analytic. Okay, maybe I'm not gonna give you concrete formula for the example. I'll just state what the main point is. So now we already discussed this intuitive fact that if you talk about equivariant volumes, right, you can take the volume of this cutting locus and then you sweep across and you get the volume of the whole space. Well, so now there's a basic claim, which actually this continues to hold at the quantum level. So the statement is that you can get the partition function of the GLSM on the full Calabi-Yau by integrating from minus infinity to plus infinity the partition function of the GLSM into the cutting locus. Okay, so this upgrades to a quantum measure, to Lebesgue measure, in the sense that you take this measure, you integrate across all values of the transverse coordinate, and you get the quantum volume. And that's fairly non-trivial if you think about it, because, okay, in the semi-classical limit, we're just talking about equivariant volume, so maybe it's a bit trivial. But then this includes all worldsheet instantons. Okay, so that's fairly surprising. And so through this relation, well, you learn that actually this quantity encodes closed Gromov-Witten invariants, because the quantum volume of the Calabi-Yau does, as Maxime reviewed. Okay, but now the main thing I wanted to say. Well, so this is a new relation that we found, but then there's another one.
So, but the C dependence of this H. Okay, no.
Yeah, it's one of the Fayet-Diopoulos parameters, because we have this additional. Oh yes, exactly. It's absolutely not. Yeah. Well, I could give you some. Yeah. Mm-hmm. I'm gauging. Is that gauging? No. Well. Yeah. It's like gauging, I guess. Probably. Yeah. 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 Can you first integrate over C? What do you mean? First, before? Yes. Okay, fine. So if you integrate first on C, then what you're left with should be should be this, right? And yeah, that would be one way to prove this. Yeah. Yeah. I mean, the main thing is you have to always be careful with contours and motion of poles. That's a slightly tricky bit. But yeah, you can play these games, and in fact, it's a very good idea to do things this way. But okay, So let me get to the end of the talk. So this is the first main formula relating, well, concerning properties of this object. But then there's another one that says that, so we can define what we call the equivariant superpotential, which is going to be some generalization of the disk superpotential for the A-brane. So we define this as 1 over 2 pi I. And again, this involves the integral of HD. But integral now goes on a cycle, so it's a closed cycle from C to C plus 2 pi I. So this is some loop in the complexified moduli space of the A-brane. Remember, this gets complexified in string theory because we have a U1 holonomy that complexifies the open string modulus. And now this function HD has many poles, so it depends where you actually take this loop, but that choice corresponds to choosing where you place your A-brane. Remember that the absolute value of C is what determines the position of the A-brane on the different legs, right? So C positive, C negative, and so on, right? So you choose a loop depending on which A-brane you want to study, and then you compute this quantity. So we call this the equivariant superpotential, and then the statement is that from this one, you can extract the disk potential of Aganagic, Clem, and Vafa as the instanton piece of the regular part. I'll explain what that means by giving you just a formula for a concrete example, and that's the last thing I want to say. So everything is very computable. In the paper, you find exact formula for C3, conifold, and local P2. So you can compute everything in all detail. But let's take again C3. Then this equivariant superpotential is fairly simple function. It's e to the 2 pi I epsilon 3 minus 1 over 2 pi I times the gamma of epsilon 1, gamma of epsilon 2 plus epsilon 3 divided by epsilon 3 times e to the epsilon 3 times c, and then hypergeometric of epsilon 2 plus epsilon 3, epsilon 3, epsilon 3 plus 1, e to the minus c. So that's the exact computation of W. Now to get this one, you have to expand that small epsilon, and then you find an expression that goes like epsilon 3 over epsilon 1 times, well, some singular piece that goes like 1 over epsilon. Then you have a regular piece that's polynomial in C. Okay, so something like C and C squared and C to the 0. That's a function, a rational function of the epsilons. And then in this regular piece, you have something that's not polynomial in C. Well, it's exponential. And so that's Li2 of minus e to the c. Okay? And then you have stuff that goes like order epsilon. And so that's, well, you recognize this is what we saw before, is exactly the disk potential as predicted by these arguments of open string mirror symmetry in the case of C3. But this is how you compute it from the worldsheet as a computation directly in the worldsheet. So, right, I'm a little bit out of time, so let me stop here. Thanks.
So questions?
Yep. Everything crystal clear. That's great.
So which other, do you have other examples?
Yeah. So you can do this in any toric labial threefold. You can choose cuts, so you can move the cut. You can choose it in different phases. So we've done explicitly in full detail C3, the conifold, and local P2, which of course is quite non-trivial. And then we also, and this is not in the paper, but we're going to look at it more in detail in the follow-ups. There's all sorts of questions related to the choice of framing for the toric brain. So as you know, the superpotential is not uniquely defined. There's some choices involved. And yeah, it turns out that everything is quite under control. And yeah, I don't want to get too much into details because it's already a lot of stuff. But yeah, you can go all the way. So you can, in the context of toric labial threefolds, the impression is that you can get all the explicit results you want, and then you can take limits and recover equivalent volumes and whatnot.
The main feature here, which is very unpredictable, that you actually get different functions, different superpotentials from the same function. So this HD is the same function for given cut. So for example, Pietro wrote for C negative, but you will do for C positive another expansion, or you will do for P2, you will get different, so you get different superpotentials out of the same function. So all monotomies of HD encodes this stuff.
Yeah.
This is a very peculiar feature.
Yeah.
Which is also very unexpected.
Yeah, so if you study, for example, the case of C3, right, we said that the mirror curve was something like, sorry, the moduli space of the A brain was this kind of Riemann surface. And if you compute what is HD, now I don't remember the formula, but it turns out that HD has a function that has singularities exactly at e to the c equal to 0, 1, and infinity, which are the three the three punctures, which is where you can put the brain, right? So then the statement that Maxime was making is that now you can take this globally well-defined quantity, and then by just studying the monodromies of this around different points, you get the superpotential in each of the different phases. But in the Aganagic-Vafa story, you have to do it phase by phase, and what you get is not even continuous. You get superpotential here, you get it there, you have to continue. Sometimes there's some factors or some even additional factors. But this is just defined everywhere. Just take it, compute the monodromy, and yeah, and once you expand, you get out. It's an integral formula, yes. But once you expand, you get their result plus some other regular pieces, which of course will have some geometric meaning. But the point really is that there's an interplay between the regular pieces and the instanton pieces that make this a smooth function that extends everywhere.
But which function is HD? And so can you exhibit as a function in some examples?
Yes. I need to get the paper or something. Did you remember? What is it? It's usually some, I think in this case, it's actually very simple. It's not even, maybe I have it somewhere. Let's see. Yes, so I have it. Yep. So in C3, I'll just give you HD. So this is for the example of C3. So this would be the integral d phi over 2 pi I from minus I infinity to plus I infinity of e to the phi c times gamma epsilon 1, gamma epsilon 2 plus phi, gamma epsilon 3 minus phi. So that's the definition of HD as a GLSM partition function. But then this evaluates, and that's the beautiful thing actually. Now you have to choose whether C is positive or negative. You're going to close your contour to the right or to the left. You're going to get two different answers. So if C is positive, you get e to the minus epsilon 2 times C divided by 1 plus e to the minus C to the epsilon 2 plus epsilon 3. So very simple function. But if C is negative, you get same prefactor, e to the epsilon 3 times C divided by 1 plus e to the C epsilon 2 plus epsilon 3. And now you say, well, okay, so you get two different functions. Too bad. But actually, here it's manifest because it's so simple that these are the same function. They're actually the same exact function. But it's highly non-trivial because you took different poles of the integrand. You close to the right, you close to the left, right? And you get the same function. And this is not an accident. It happens in all examples. So when you go to conifold and local P2, of course, you don't get something so simple. There will be some hypergeometric factors of T dressing this up. But again, you look at different phases, and no matter how you close, you get a function that's an analytic continuation of the other one. So it's
Other questions, other comments? Otherwise, we go through. In the beginning, you mentioned not zero. What's the implication of symplectic function to the non-zero?
yeah, very good. So short answer is I don't know. Yeah, I don't know. But I'll tell you one thing. So these cuts that I described, they're very, very simple. They're suitable for toric Lagrangians, right? Because they're defined on hyperplanes, and hyperplanes are associated to toric Lagrangians. So there's one toric Lagrangian that corresponds to a knot, actually. That's the L knot. So there's an implication there. You can study the toric brane in the resolved conifold. That's going to give you knot invariance for the unknot. So you could do this story, and yeah. But more generally, the kind of Lagrangians that are associated to knots, they're not toric Lagrangians. They're much more complicated. So you cannot use this type of
For any knot, you can associate some Lagrangian.
Yes, some
not necessarily toric.
not toric. But it will have topology R2 times S1. Yes, and it's in the resolved conifold. So this is some construction. But yeah, but these Lagrangians, their geometry is much more involved than the toric Lagrangian. So you will not be able to use this kind of symplectic cuts, just flat hyperplanes. However, if you go back to the original paper of Lerman, so Lerman is the person who defined symplectic cuts in '95. He actually describes a more general notion of symplectic cut, which can be based on just purely Lagrangian data. So there's a way of cutting along Lagrangians as well. And I think in the math literature, there's been some developments on open Gromov-Witten theory in this setting. Yeah. But that's all I know for now. Thanks for the question. Okay. Thanks.